of how we use the Gauss law to obtain the electric field as a function of the given geometry. Now we can assume another example, and now these examples that we are going to provide today, they are mostly just to see how we can calculate the potential and the electric field. In one way, you can also report it in this way. We are kind of learning how to do integration in the best way possible. Okay, so we are learning how to integrate. That's how we might assume this. So initially, let's think for a moment, if we have a ring, and when we say it's a ring, it's just a wire. Okay? It's a wire which has a uniformly distributed charge Q. Uniformly distributed charge Q, and radius is equal to R. Find V at the distance L. Okay, so let's pose the problem like this. So the distance is L. That means from the center we are at the point P, distance L. How can we solve this one? What we should know is that we can, from this expression, V is equal to K Q over R. What we can derive from here is that we can express that the infinitesimally small potential, which is going to be originated from an infinitesimally small charge distribution, delta Q, this can be written as follows: dV is equal to K dQ over R. Okay? So often we need, the major question for us is the following: what is dQ? Okay? So now this is dQ, and then what we need to do is that once we write this expression, we have to do the following: we have to integrate dV. Okay, and then let's see what we obtain. We see that the potential is equal to, so the charge is allocated along this path, okay? And now the radius is R, so let's write this down. This is the radius R, and this R, this stands for the distance from the charge to the point of interest, okay? So now we know L, we know R, at this distance it can be written as, so this is potential is equal to the integral of K dQ R. This can be expressed as R plus L squared whole square root. Okay, and now in this expression, R and L, they are constants, so we can take them out of the integral. We can get here K over R squared plus L squared integral of dQ. What is the integral of dQ? Integral of dQ, I like to think of it as if they are inverse functions of each other, which means that the integral of the differential is equal to Q itself. So we have the whole Q, and then as an answer, we get that the potential is equal to K capital Q R squared plus L squared square root. Okay, this is all that we need to consider. Let's see another example, and we will try to draw equivalent principles from this example and the next one. And in this other example, we assume a disk which is filled. So let me write it like this: filled disk. This one, it was a ring where the charge was distributed only around this path. But now we have a disk which is completely filled, and it has sigma. When we say sigma, it has charge density over meter squared. Okay, and here we can say that the rho, the charge density, the unit of charge density, is coulomb per meter. Okay, it's worth putting this down because it reminds us of the geometry and how the charge is distributed. So field disk having this coulomb per meter squared, we need to find the potential at the point P. At the point P, right here, where P it is at a distance equal to x, and we need to find the potential again. So how can we find the potential? We need to write, so potential as this expression, then we can express this, okay? But now, we have to figure out one way how to calculate the potential as best as possible. And for this one, selecting an infinitesimally small charge element, it can be allocated right here, okay? So this can be our charge, but how can we describe this? Now, if the charge density is uniform, which it is in this case, then we can do the following. If the surface area of the disk, it is pi r0 squared, and the total charge is equal to q, then what is the charge if the area is 2 pi r dr? Okay, because this element that we see here, the language that we can construct is the following. At radius, I think we mentioned this one before, at radius r, select an element dr, okay, thick. So pick up at the radius r, select an element of dr thick. So, and we draw this element which is shown here, then we can see that, in fact, this is dq. So our initial question is to figure out what is the charge element which is located here. And let's draw this is r, and then we can say that dq is equal to 2 pi r dr divided by r0 squared q. Okay, these can cancel out, and then we can write here. This is 2 q r over r0 squared dr. So this is the dq. Now that we have this the dq, we have to start taking the integral. So, and this integral, it has to be considered that the distance from this point, so all of these points which we can find across this path, they are all equidistant to point P, okay? So they are equidistant to point P, then we can simply write that dV for the voltage, this is equal to K to QR over R0 squared. Wait a second, so this is 2QR over R0 squared dr. So let's not forget, this is just dq. Okay, so this is dq. And this dq, it has the delta r inside, divided by r. Now r is the distance from these charges down to here. So this will be equal to 1 over the square root of r squared plus x squared. Okay, let's notice that x is a constant value, but r is changing. Okay, so this is the dV. Then the potential itself, it is going to be, probably we can use this part of the board here. The potential, the V, is going to be equal to the integral of all of these expressions. And for the integral here, we can keep out of the integral all the constant terms. So here we can have 2k, q, it's a constant, anything else? No. Then here we have over r0 squared, and then inside the integral, we just have dr over r squared plus x squared, r squared plus x squared. And then, in order to get this integral, we just, wait a second, we have any notes? I've forgotten something. Please remind me, there is a little r here, okay, because this r appears here. So this is r dr, and for this integral, we can do a change of variables, and the change of variables might include the following. So we can say u, it's equal to r squared, which means that du is equal to 2r dr. Okay, so if we describe it like this, things actually we can also do it like this: r squared plus x squared. Maybe this is better. So u can be r squared plus x squared. Wait a second. And du is equal to 2r dr. Yes. And then from this pair here, we can say that r dr it is equal to du over 2, and finally, this can be written again as 2k cubed over r0 squared. This 2, we take this out because r dr is now du, okay, divided by square root of u. So square root of u, or square root of u, and the integral of the square root of u is equal to what? We know that the integral of u to the power m is what? It's u to the power m plus 1 divided by m plus 1, right? Now, m, which is the power of u in this case, is what? What is m here?
Minus 1 over 2.
Minus 1 over 2. So here, m, which is equal to minus 1 over 2. This means that the integral of minus, or let me write it like this. The integral of 1 over square root of u, this leads to square root of u, so this is u to the power 1 plus 2 over 1, wait a second. What is this? Minus 1 over 2 plus 1, 1 over 2. So we're dividing by 1 over 2. So this is equal to 2 times square root of u. 2 times square root of u. By the way, these 2's cancel out, and then we have 2 times square root of u, and this will be equal to 2k cubed over r0 squared. This is r squared plus x squared, r squared plus x squared, and the integral, it should be from 0 to r0, okay? So this will be the limit of the integral, and then we are going to write here that this is equal to 2k cubed over r0 squared over, sorry, we have a mistake here, this is square root of u, right? Because this is square root of u was this whole terms, then this is going to be equal, this is square root of r0 squared plus x squared minus x. Okay, so this is the expression that we obtained here. Okay, that's good. This is equal to the potential. Okay, now this is the answer, and this is of course the answer for this disk, and we're assuming that this disk is full with material, or full with charges everywhere. Now, we can consider a special case if x is much larger than r0. So this was just to assume x is much larger than r0. So often we may have to use these approximations to see how the values are changing. So if x is much larger than x0, what we can do for this is that we can factor out the x here. So we can say v, it's equal to 2k cubed over r0 squared times, so here we can factor out x. So this is x times 1 plus this is minus x, and in this expression we have that sorry. So in here we can use a relationship that 1 plus epsilon to the power n is equal to 1 plus n epsilon. Okay, so that's an approximation. In this case, if x is much larger than x0, then epsilon is r0 squared divided by x squared. Okay, so that's the term. In this case, if we have 1 plus epsilon to the power 1 over 2, this is approximately to 1 plus 1 over 2 epsilon. Okay, so this is the approximation. In this case, as we said, what was our epsilon? It was 1 plus 1 over 2 r0 squared over x squared. Would you agree with this? Okay, let me look at it for a moment. Yes. Okay, so then let's move on. This is equal. We have here 2k cubed over r0 squared multiplied by, so this square root, which is here, this can be written as x times 1 plus, or you know what, let's multiply it like this. So x is multiplying this 1, that's there, plus x times 1 over 2 r0 squared over x squared. So I multiply with x, the second term, minus x, and this is equal to, so I think we can cancel these x's together, and this is equal to 2k cubed. Now this r0 squared is cancelled with this term here, and we're left with this, we get another 2, which is coming from here, or better, let's do it like this. Let's give this 1 times 1 over 2x, right? Because this x cancels x squared, that's what we are left with. And this is equal to 2's go out again. And apparently, the v, it is going to be equal to k cubed over x. Okay? Have we seen this expression before? Most probably yes, because this one, it is very, it's the same with this expression that we observed here. Okay? And this approximation, what this means is that if x is much larger than r0, we can be so far away from this disk that this disk can be considered as a point charge. Okay, so it is a disk, fine, but we can use these approximations here, and it's also imperative that if we are too far and we cannot distinguish the exact shape of this disk, that's what we can write. Okay. So this was the integral that we obtained there. Okay. Then Okay. Now we are calculating the potentials and the electric fields from a charge distribution, but we should relate together both the electric field. Wait a second. Actually, just for a moment, let's keep here. Let's keep this potential for a moment here. Okay, so this is the potential. That's good, and that is as a function of. Wait. We integrated it, and we wrote this one as a function of x. Yeah. So just for a moment, R0, it was a constant value, and we followed, so what this is yes, V is equal to V of x. So apparently, for a total charge in a system, we observe that the potential, it will depend like this as a function of x. And a possible question is the following, is what is E as a function of x? Okay. So this is a good answer. And regarding this, we can say that the electric potential, it is equal to, or sorry, the electric field as a function of potential. It can be written as follows. So this is equal to minus the del operator times V. Okay. So this is the del operator, and in this case, let me think for a moment, we can also compare these expressions where V, it is kq over r, and in this case, delta V over delta r, this is equal to kq, and r to the power minus 1, it is minus 1 over r squared. So this is equal to kq with a minus over r squared. And this means that the electric field is equal to minus the delta V. And if we substitute this expression here, we get that the electric field, it is kq over r squared. So for a point charge, for the potential, and for the electric field of a point charge, this expression, we somehow confirm it. Okay, so we are good. Now, what we can do, again, to check this expression is also the following. Let's not erase this one for a moment. Let's assume that we have the same geometry, and we need to find, so we found the potential, everything is good. We have the delta Q here, everything is still okay. So what we can try to do next is try to find the electric field in this geometry using two different techniques. One technique, it can be by trying to identify the electric field intensity. And how would we do that? How would we do that? It will be like this. So we are at some point here. This is the distance x. And the charge, so the electric field, which will be created here, it is delta Ex. Okay, it is going to be a vectorial quantity, but how will it be written? This delta Ex, this is equal to k dq over r squared, and r squared is the distance from this point down to here, and this will be equal to k dq. It is this whole expression here. Okay, so I'm not going to write it for the moment. And this one, it will be divided by r squared plus x squared. So this is the dE. Do we need to do anything else? We can try to simplify this a little further. Maybe not. So dq is given. So we can, let's substitute this dq into this expression. But just for a moment, this is, yeah. So this will be equal to k times 2q over r0 squared r squared plus x squared. Okay, so this is the dE. Now, the electric field would be equal to the integral of dE, which means that what are the numbers, the values that are constant? We can take them out. This would be 2qk over r0 squared, integral of r dr over r squared plus x squared. Okay. Then probably we can use a similar change of variables. U is equal to r squared plus x squared. Sorry for erasing this one. And du would be equal to 2r dr. And this r dr, this will still be equal to du divided by 2. And then our integral, it will include the integration of, so let's see what we'll obtain here. So we have here 2k cubed over r0 squared times, instead of r dr, we write du over 2. So we can even write this one right here, du over 2 times, this is u itself. So they cancel out, and the integral of du over u is equal to what? What is the integral of 1 over u?
ln u.
ln u, that is correct. That is ln u, and here we'll have here k cubed over r0 squared, ln u, and u is r squared plus x squared. R squared plus okay, but we have to integrate from 0 to r0. So this is from 0 to r0. So this is the electric field. Okay, so that's one way to find it, but now we can go back and try to identify what is the so we find this expression, you can apply the limits and see what we obtain. But now for a moment, let's assume that we have this potential, and we want to find what is delta V over delta X. And delta V over delta X, we mean this. So let's try to do this calculation. And in here, first of all, we have to identify the constant values. So we get here 2k over q, sorry, over r0 squared times the, what is the derivative of r0 squared plus x squared? So let's write this here. So this is r0 squared plus x squared to the power 1 over 2. And we need to find the derivative of this one with respect to x. So this is d over dx, and this is equal to 1 over 2 times this is minus 1, this becomes r0 squared plus x squared multiplied by the derivative of this internal term here. So this is going to be 2x. If this is wrong, please correct me. But these twos, they cancel out. And here, we're going to have the following. Times x divided by r0 squared plus x squared. Okay, this is what we have here. And then minus 1. Wait a second, minus 1. Yes, that's what we obtain. And then the electric field here, it should be equal to the negative. Do we have any other terms here? No. I believe. So this is equal to 2k cubed over r0 squared, 1 minus x to the r0 squared plus x squared. Okay. This is the derivative or the expression for this case, or at least when we implement in this case. Now, similarly, we can also say, based on this expression here, we can say that the change between any 2 points, this is equal to the negative of the integral from point P1 to P2 of E dot dl. Okay, so from this expression, this is what we can also find. Now, in this case, wait a second, how much time we have left? We have some time. Okay. And what we need to stress here is that whenever we try to find the potential at some point, we have to calculate the value of the potential based on some reference point. And in fact, the best reference point for the potential that we can always use is to use the value of the potential at infinity. Okay, so and that value of the potential is equal to 0. That's why if we have a complex system, we always try to use the infinity as 0. So, and then we integrate backwards. With the integration, we mean an expression that looks like this. And if you remember, the energy that we calculated for a system which was composed of 2 charges, what we did, we integrated the force dot the distance from infinity to some point of interest. Okay, so that's what we did. And we were sure that the force between 2 charges, if they are far away from each other, is going to converge to 0. Now, let's see another example, and probably we can erase this one. And see an example as follows. So let's assume we have a charge Q inside a conductive shell. And this conductive shell, it looks like this. And this has an inner radius Ri and an outer radius Ro. And so this is the conductive shell, and this is the charge at the very center. Okay. The question is this. So this is the question. Find the potential and the electric field as a function of radius for this configuration. Now, to do this, what we can try to do is that, as we said before, we can use R equal to infinity. This is not a true expression, we are close to infinity, as a reference. Because we know for sure that the potential, when R diverges to infinity, the potential converges to 0. So that's how we can write it. So initially, let's consider when R is larger than R0. In this case, we can draw a Gaussian surface, and the Gaussian surface will be what? The Gaussian surface will be somewhere here. So let me draw it on this side. So this is the distance R, and we need to do the following: E times 4 pi R squared. This is equal to the Q enclosed divided by epsilon 0. And the Q enclosed, it is the charge Q, which is placed right at the center in here. Okay, so this is vacuum, this is conductive shell, and this is vacuum again. Okay, So we did not draw this everywhere, but this will continue like this. So it looks like for the first case, or in the first region, the electric field in this region beyond the R0, it can be written as kq over r squared. So E is equal to k capital Q over r squared. This is the first thing that we can include. And then the potential in the same region, it will be as follows. So we're going to say VR minus V at infinity, using a similar expression like in here. So we have VR minus V infinity. This will be equal to the EDL, the integral of EDL. And for the expression, now in this case, dl is the radius r, because we are assuming that we are approaching from one point to another by decreasing the radius r. So here we have, let's think for a moment. So we have v minus v1. So Vr minus infinity, this is equal from infinity to r with a minus sign, okay? And then, if this is the case, let me think for a moment, Vr, yes, I think that would be the case. And then we get minus kq over r squared dr with a minus sign. What we are going to obtain is that we're going to get kq over r. So this will be the potential out of the R0. So this is R inner, this is R outer, or RO. So this is the potential for R larger than R0. Then what we can do is that we can go over another region, and this region is between Ri, R inner, and smaller than R outer. So that means that we can come in this inner region, but if we come into this inner region, we are going to get this Gaussian surface, okay? So the Gaussian surface is here now, okay? It's in this region. But now we know that inside the magnetic shell, the electric field is equal to 0. So immediately, just because we know this, we can say that the electric field is equal to 0. Now, if this is the case, we can also write this expression again, which will be E times 4 pi r squared. This is equal to Q enclosed over epsilon 0. But if this is equal to 0, it has to be because it's a conductor. So imagine for a moment, you equal this to 0, and immediately you also get this 0, which implies that the enclosed charge is 0. Okay? But being the enclosed charge equal to 0, what this means that the charge at the inner, right here, it's equal to minus Q. So here we're going to get negative charges everywhere in here. Okay, and all of these negative charges, the summation of all of these is going to be, so let's write it like this. This implies that the Q inner, this is equal to minus Q. Okay, why is this? Because here we have a positive Q. At the inner boundary, right here, we should have a negative Q, so that the total charge inside the Gaussian surface is equal to 0. But if this is the case, we can also say that the outer Q is equal to plus Q. Okay, this is a conductive shell, and then it looks like the charges can move within this conductive shell, and they do. And then we have a negative charge in the inner boundary, which is equal to minus capital Q. And we have an outer charge in the outer boundary, which is plus Q. So this is how we can visualize this system. Now, Another thing that we can conclude from here is that the conductive shell, assuming that the electric field is equal to 0, then this is equipotential. Okay, so potential at V outer is equal to potential at V inner. Okay, so we are using this notation. This is the inner radius, and this is the outer radius. And then, so we said the conductive shell is equipotential. Then we can say that the potential at R equal to R0, this was equal to K capital Q, not R0, this is R outer. So let's write it like this. Okay. Then now we come to another region, which is the region inside the conductive shell. So R smaller than R inner, and in this case, what we can say is that the potential V3 is equal to the potential V3 is equal to minus EDR plus a constant K, okay? Plus a constant K, but this whole expression, wait a second, this is electric field is K over R. Actually, before we do this, let's find, sorry. So in all these cases, actually, we only started by finding this electric field, okay? And then we also discussed here to find this electric field here. And maybe it's better, because if we don't show this one, it might be difficult to pick up this information here. So again, let's assume for a moment, or let's try to find what is the electric field here in this region. And the electric field will have the same expression, E times 4 pi R squared. But let's notice that the value of R, it is going to be smaller than this inner radius, okay? And this is equal to Q over epsilon 0. So the electric field will be K Q over R squared, or where K is equal to 1 over 4 pi epsilon 0. So these are identities which are known, the relationship between different constants. And in this case, the V3, so this is the electric field which will be used in this expression also. And this will be the potential at any point inside the conductive. So the potential in this region at any point, it will be described as K Q over R plus capital K. But here we have to consider also at this point that so what we have to say here is that as we are coming from infinity, where potential was equal to 0, at this outer boundary, the potential will be equal to this expression, but we have to evaluate it with substituting this little r with r0. Then we get this expression. But since this conductive layer, it was equipotential, we can say that this V inner, it should be equal to V outer, because the potential at this point, here, and everywhere, they are all equal to each other. So then, when we come to this expression here, we have to say that the V3, which is when radius is equal to R inner. Okay, so let's try to express this one. And when we say R inner, we want to see how these constants change and or we want to use this boundary condition right at the inner radius in here. Okay, so let's see what we get. This V3, it's evaluated at R inner. This would be equal to KQ over R inner plus a constant K, and this is all equal to KQ over R outer. Okay, so we need a constant now. This is a constant of integration. So we know that always when we are integrating, we're going to get the constant of integration, but for this relatively complex problem, it is good if it is better if we approach like this way. So it looks like KQ over R inner, this is the expression that we get from here, plus this constant should be equal to this specific value. So at this moment, what are we using this expression for? We are using this expression to determine this constant of integration K. Okay? So, and this constant of integration K, in this case, it can be written as KQ 1 over R out minus 1 over R in. So this is our constant of integration, and the complete expression then for the potential in region 3, it can be written as KQ 1 over R plus this other K, which is plus 1 over R outer minus 1 over R in. So this would be the complete expression for the potential V3. And now in this expression, or these relations, what we can see is that the potential, this is R inner, this is R outer. We observe that the potential, so some point here, we said that from R inner to R outer, this was a constant value, and here, this decreases like 1 over R, this is constant, and this is decreasing like 1 over R again. But the electric field, we notice that when the electric field is at the outer regions, let's do this one with a different color, this is going to change as whatever the electric field value is. Let's draw this, or let's assume that we are reading the electric field on this other axis. So here we have the potential. They are not on the same scale for sure, because they are different quantities. But the electric field here, it is going to decrease by 1 over R squared. Here, the electric field is going to be equal to 0. Okay, so we have to pick this up like this. And here, this is going to be, so in red, we have the electric field, and in black, we have the potential. Now, what we see from here is that we have to be very careful whenever we try to determine the potential, because the potential, it's a quantity where you always need to determine a reference point, okay? Now, do you have any question here?